Hello everyone. Today we are going to study the third part of instruction set of 8086/8088 microprocessor. Earlier in the topic on how 8088 works, functioning and working mechanism of 8088 microprocessor was discussed, and later in a topic on instruction set part 1 we discussed the data transfer and add instruction and its variants. As we have studied earlier that an instruction set of a microprocessor defines the basic operations that a programmer can use and design programs using these instructions. The 8086 microprocessor provides powerful instruction set containing 117 basic instructions. The basic instruction has a wide range of operands and addressing modes available, so that the basic instruction expands into many more instructions executable at a machine level. In the earlier topic on instruction set, we have studied instructions related to data transfer, arithmetic and logical instruction, shift and rotate instructions. Today we are going to study the instructions related to setting of various flags, instruction called compare, jump and call instructions. These instructions are broadly classified into two categories: unconditional and conditional branch instruction. The unconditional branch is made through jump or call instruction. When the instruction jump address is executed, the control of the program is transferred to the address specified along with the instruction. However, the transfer of control in a conditional branch instruction is based on the condition specified. The condition is determined by the status of the flags. The flags can hold a binary value true or false and is represented by a single bit in the microprocessor. The 8086 microprocessor has a set of flags that are indicated by a single bit value in the status bit register. These bits are changed when an arithmetic or logic instruction is executed. The change in the bits or the flags of the status register depends upon the value of the result obtained. For example, if the result of an add operation is 0, a Z flag is set to 1. The jump and call instructions make use of the status flags to decide whether to transfer control to a specified location or not. The 8086 microprocessor has a group of instructions that directly affect the state of the flags. These instructions are called flag control instructions. Under this group, an instruction load AH, that is load the contents of the register AH from flags. This instruction is abbreviated as LAHF and it loads the AH register from the lower 8 bits of the status register, which is a 16-bit register in 8088 microprocessor. The instruction SAHF on the other hand stores the contents of 8 AH register into the lower 8 bits of the status register. The flags 0, 2, 4, 6 and 7, that means in the position of 0th, 2nd, 4th, 6th and 7th bit containing carry flag, parity flag, auxiliary flag, 0 flag and signed flag in the respective bits of the status register are affected by this instruction. The new value of flag is taken from the register AH. The instruction clear carry, in short defined as CLC. CLC is the abbreviation of the instruction clear carry flag. It clears the carry to a value 0. The instruction set carry STC sets the carry flag to a value 1. The instruction complement carry, in short CMC, complements the carry flag. That means it reverses its status from 0 to 1 or vice versa after the execution of this instruction. The instruction clear interrupt flag CLI clears the interrupt flag. That means, it sets the interrupt flag to 0. The instruction STI sets the interrupt flag to 1. The next important instruction in 8086 is compare instruction. The compare instruction can be used to compare two 8-bit or two 16-bit numbers. The format of the compare instruction is CMP D, S. D stands for a destination register, S stands for a source register. The instruction performs a subtraction operation, D minus S. That means, the contents of the register S are subtracted from the register D, and then the result of the subtraction operation is not stored anywhere. However, all the status register flags as a result of subtraction are affected by this compare instruction. The operands D and S in the CMP instruction could be a register pair, register memory pair, or a register immediate pair. Assume the program instruction sequence move AX, 3456 hex, as AX is a 16-bit register. So, we are storing a 16-bit value in the register AX. The second instruction say move BX, we store a value CD, EF hex, and then we perform compare AX, BX. The first instruction loads AX with value 3456H. The second instruction loads CDEF into BX register. The third instruction compares AX and BX by applying an operation AX minus BX. The carry flag is set to 1 because the AX is less than BX. Similarly, the auxiliary flag is set to 1 as during the process of subtraction a carry bit is generated from 8th bit to 9th bit. Since no overflow occurred during this AX minus BX operation, the overflow flag is set to 0. The result of the subtraction operation is not 0, so the 0 flag is set to 0. As said earlier, the 0 flag is set to 1 only when the result of the operation is 0. The sign flag is 0 as the most significant bit of the result contains 0. The parity flag again is 0 as a result of subtraction. The next category of instruction in 8086 microprocessor is jump and call instructions. The purpose of jump instruction is to alter the execution path of the instructions in the program. In 8086, the code segment and the instruction pointer keep track of the next instruction to be executed. Thus, a jump instruction changes the contents of these registers, resulting in the transfer of control to a new location. The program instructions will then be fetched from the new location. In this way, the instruction execution continues at another address instead of the next instruction in the sequence. As explained earlier, the microprocessor 8086 has two different types of jump instructions. These jump instructions are conditional and unconditional jump instructions. In unconditional jump is to the specified location takes place without any specified condition. In the program, the instruction jump ABCD jumps to the program statement specified by the label ABCD. On the other hand, when a conditional jump instruction is there, the jump takes place only when the condition specified with the jump instruction is true. If the condition is false, the execution takes place from the next sequential instruction of the program. The unconditional jumps are further categorized into inter-segment and intra-segment jump. If the jump is within the same segment it is currently executing the program, it is referred to as intra-segment jump. The intra-segment jump is achieved by just modifying the value of instruction pointer register without changing the contents of the code segment register. If the jump is outside the segment boundary, it is referred to as inter-segment jump. The inter-segment jump permits jump from one code segment to another and therefore requires the modification of contents of both the registers, code segment as well as the instruction pointer register. The format of the jump requires a specification of a 16-bit operand stored in the register or a memory location for intra-segment jumps. An inter-segment jump format requires a specification of 32-bit pointer expressed through a memory pointer. The first 2 bytes of the memory pointed to by the memory pointer are stored in the instruction pointer IP register, and the next 2 bytes of the memory location are brought in the code segment register. In all, 4 consecutive bytes are fetched from the memory location pointed to by the memory pointer. The conditional jump instruction also works on intra-segment as well as inter-segment address. The different types of conditions associated with the jump are related to the status of various flags in the status register. For example, the conditional jump instruction JC checks the carry flag, and if the carry flag is set, it performs the jump to the specified location as specified by its name, jump if carry, which is JC in short. Another instruction, JCXZ, performs the jump operation only if the contents of the register CX are 0. The instructions JNC and JNCXZ perform jump if no carry or CX is not equal to 0. Another instruction JZ performs jump only if the 0 flag is set to 1. Similarly, the condition of all the status flags can be used as a condition in the conditional jump instruction. The condition can be specified for both the value of flags as 0 or 1. This is all about the jump instructions. Both we have covered conditional as well as unconditional jump instructions. Next are the instructions related to input and output. For example, an instruction in AL, 15H stands for the input data from port at address 15H, and these ports are connected to external devices. That means, if some external device which is an input device puts some value at the port number which is connected to port number 15 and it puts some value at port number 15, that value can be read by the microprocessor through the instruction in AL, 15H, and after the execution of this instruction, the 8-bit result available from the port number 15 is stored in the register AL. The port address can be specified as an 8-bit number, and therefore, theoretically 256 input devices are supported. That means, theoretically we can connect 256 input devices with the microprocessor 8088 or 8086. Also, consider the instruction in AL, DL specifies that the input byte wide data from port address specified by the contents of the register DL are brought into the register AL. Similarly, the instruction out AL, 15H transfers the contents of 8-bit register AL to the port address 15H. That means, if you have connected some output device at port number 15, the microprocessor write the data to port number 15 through the contents of register AL. The port address can also be specified indirectly by the instruction out AL, DL. The contents of the register AL are returned to the port address specified by the register DL. As we have studied earlier that the memory area pointed to by the address SS0 is used as a stack segment. The stack pointer in the 8086 microprocessor is indicated as SS0, SS is a 16-bit register, and then 0 hex, that means it is equivalent to 4 binary bits, and if the contents of SS appended with 4 binary bits making it a 20-bit register is added to the 16-bit stack pointer register, overall that 20-bit pointer becomes the stack pointer in 8086 microprocessor. Related to stack, there are now two instructions, push and pop. The push instruction can operate on an 8-bit operand or a 16-bit operand. For example, a push CL is an 8-bit operation in which the contents of the CL are stored on the stack and the stack pointer is decremented by 1. Whereas, a push BX is a 16-bit push operation. The higher order 8 bits of the register BX are stored first, followed by the lower order 8 bits of the register BX, which are BL. In all, the stack pointer after the push BX instruction is executed is decremented by 2, because we are storing 2 bytes on the stack. The pop instruction also uses an 8-bit or 16-bit operand. For example, pop CL is an 8-bit pop operation in which the contents of the top of the stack are transferred to the CL. That means, now the pop results in the contents of memory location which is pointed to by the stack pointer to the register CL, if it is a pop CL operation, and the stack pointer in case of pop operation is incremented by 1, whereas the pop BX is a 16-bit pop operation and the top of the stack contents are copied to the lower order 8 bits of the register first. Next, the stack pointer is incremented by 1, so that the next byte is copied into the higher order of higher 8 bits of the register BX. In all, the stack pointer is incremented by 2 by a 16-bit pop operation. Next are the instructions of 8086 microprocessor related to subroutine call. The subroutines are the procedures written separately from the main program. The main program, in order to execute the code within the subroutine, calls the subroutine with the call instruction. When a call is made to the subroutine, the program control is transferred to the beginning of the subroutine. When the last statement of the subroutine is executed, the program control is transferred back to the next statement of the main program written after the call to the subroutine. The difference between the subroutine call and the jump operation is that the call to the subroutine not only produces a jump, but also saves the information on where to return after the execution of the last statement of the subroutine. There are two basic instructions available for handling subroutine calls. First is call instruction and second is return instruction. Similar to jump, call can also be intra or inter-segment. In case of inter-segment call, a 32-bit register pair are saved on the stack. First, the contents of CS are pushed on the stack, followed by the contents of instruction pointer are pushed on the stack. Stack pointer is decremented by 4 bytes. In case of intra-segment call, the jump is within the segment and therefore, only the register contents IP is stored on the stack. The stack pointer is decremented by 2 bytes. The return instruction, which is written as a last statement of the subroutine, it makes use of the top of the stack to return to the next statement written after the call to the subroutine. In case of intra-segment return, only the top 2 bytes are popped from the stack and assigned to the instruction pointer. In case of inter-segment return, top 4 bytes of the stack are popped. The first 2 bytes are assigned to IP and the next 2 bytes are assigned to code segment. The stack pointer is incremented by 2 or 4 depending upon whether it is an intra or inter-segment return. An intra-segment jump needs a shorter address. So, what we have learned today are the various instructions of the 8086 related to compare, jump, call and input output, how they are executed. The instructions related to jump and call were discussed. The issues of intra-segment and inter-segment were elaborated. The input output instructions and instructions related to stack like push and pop were explained with examples, and using the stack how the call instruction is executed or how the call instruction maintains the return address and which is used when the return instruction is executed, and how the call instruction helps us to implement the subroutine calls in the main program was discussed in this topic. Thank you.